Okay, we're up as far as describing a typical old style valve microphone.
Yep.
With modern addition in the case of the Classic 2. Let's go back to basic Electret mics.
Yep.
As found everywhere, which don't have bias, which don't have tube amplifiers. They do actually have buffers, but they don't have output transformers.
Nope, none of that rubbish.
Yep, and in fact
So these are our little 10-cent mics that we find in everything.
So we'll do... now, the solid back electrode might be at ground, or it might be the actual hot electrode, if you like.
Right.
The diaphragm might be at ground, or it might be the hot. We don't know. The electret, to polarise the Electret mic might be on the diaphragm, or it might be on the back plate. Doesn't particularly matter. We'll just draw it that way for convenience. And what we've got there is a thing where when we talk at it, we get volts out of it.
Yep.
But as transducers go...
What type of level are we talking?
Let me think. Typically, they're around about minus, let's call it minus 45 dBV per Pascal, which translates to, let me see, minus 40 is 10 millivolts, so minus 45 is probably about, I don't know, 4 millivolts or something like that. So maybe 4 millivolts. Get it right, lad. 4 millivolts at 94 dB SPL.
Right.
Give or take a bit of poetic license. That could be minus 35, could be minus 50.
Got it.
Okay, so if it was, say, minus 40, that would be 10 millivolts at 94 dB. 94 dB corresponding to 1 Pascal. Incidentally, that's the usual format for mic manufacturers to specify sensitivities. So you have to do the translation of that to there and that to there.
Yep.
Me. Okay. Now, what can you do with a transducer that's putting out, well, 10 odd millivolts with a source capacitance of maybe about 5 puff? Well, let's kick off by sticking it into a JFET, because that's what everybody does.
That's what they do. They stick them right on the back there.
Yep. So, JFET.
And that's pretty much all.
That's just about it.
Yeah.
Now, in the good old days, we'd actually see a discrete bias resistor there to hold the gate near 0.
Yep.
That would be a gig-ohm-ish resistor.
Right.
There are, well, how do you put it, 2 different basic electrical styles of Electret mic. In one of the styles, that, and that are all bought out as separate electrodes.
Yep.
The idea being that you can put a voltage on there, hang a load resistor off there, and there's your AC voltage with some DC superimposed coming off there.
Sure.
Rarely done, even though generally that particular topology offers better linearity and higher SPL handling and all of that kind of stuff. Usually not what happens. Usually what you get is...
Are they using Electret mics in any pro applications?
Yes, yes.
Whereabouts?
There are a few stage microphones, which are back Electret types. Even companies like Sennheiser and AKG are offering stage and recording microphones, which are Electret.
To what advantage?
I think the main advantage is they're cheaper to manufacture. There's less electronics in there to go wrong. Yep. You know, the bias circuitry, etc. And you can use them over a wider range of incoming DC supply voltages.
Got it.
One of the areas where you'll see lots of Electrets used in preference to externally polarised is whenever you see a skinny gooseneck with a little head on it, as used in courtrooms, panels, Parliament, that kind of thing. They're all going to be Electret. And the usual players such as Shaw and Sennheiser and AKG, they're all going to be manufacturing that style of thing.
Right.
Most of these look like that.
Yep.
That beastie there, JFET, becomes a voltage to current transducer, so it's a transconductance device.
Yep.
So all of a sudden now what you're seeing here is not a given number of volts per pressure,
yes.
It's current modulation per pressure that only gets turned back into a voltage once you add a load resistor.
Doesn't work without it.
Correct.
And then you AC couple off that?
Yeah.
Yep.
And in fact, for some reason, one of the standards is to, when they're specifying the sensitivity of these mics, their standard is to use a 2K resistor.
It is, I've noticed that.
Simply because it forms a common base for everybody with a 5 volt supply.
Yep.
And it just gives everybody a common basis, a common platform from which to work.
Although you can operate them much lower supply voltage.
Yeah. Now, let's have a look at the...
Single cell, 1.5 volts.
Yeah. With caveats, caveats.
I've got one right here in my pocket. Runs off a single coin cell. That's it.
Oh, mind you, 1.5 or 3 point something volt coin cell?
1.5.
Okay.
1.5 volts. There you go.
Much depends on the characteristics of the FET.
Yep.
Let's have a look at the current versus voltage characteristics of a JFET, measured voltage there, current through there, zero bias on the gate.
Right.
Most of them will have a characteristic that looks like that. Once you get above a certain voltage, about there, that thing produces a constant current source.
Right.
And it's in this region here that you want to operate the FET.
Yep.
Why? Because as soon as you start coming down into this part of their characteristics, the gain, the transconductance of that just goes to putty.
To shot. Yep.
Now, I went through a stage of measuring rather a lot of different Electret mics. That gain reduction point varied from FET to FET, from FET type to FET type. Most of them were good down to around about 1.1 or 1.2 volts and would then plummet. There were some better FETs that would come down to maybe 0.8 volt before they started rolling off in gain.
So you could run those off a single alkaline cell until they're dead?
Yes.
Practically.
So for example, let's take a typical JFET that might have a constant current region where it draws about 350 microamps, and that's a very, very, very typical figure.
It is.
For the JFETs used in Electret mics. Let's say up here we've got a single cell at 1.5 volts, and let's say that that particular FET would maintain its gain down to say 1 volt, just to make the numbers easy.
Yep.
Okay. What value of resistance can we reasonably put there in order to get those conditions? Well, we've got half a volt across it, we've got 350 microamps through it. R equals 0.5 volt over 0.35 milliamp, and at a rough guess that's probably going to be about 1.4k.
Something like that?
So you might actually toss in a 1k resistor, which means that that battery can be depleted to 1 volt plus 0.35 volt
Yep.
before it starts losing gain.
Got it.
Or you'd pick a FET that instead of having a knee point at 1 volt went down to say 0.8 volt and maybe drew less current. Now, you can make that resistor smaller. That will allow you to flatten the battery further before you get gain roll off.
Yep.
Penalty, the lower the resistor there, the lower the signal gain to that point there.
Of course.
So it's all a compromise. And of course, if you've got a few more volts available, beauty, you don't have any problems anymore.
Absolutely.
But I guess anybody who's using an Electret mic in a new piece of equipment needs to know what voltage they've got available so they can plan what resistor they use.
Yep.
So for example, if you've got a piece of kit with a 5 volt supply, okay, let's just do this again, but this time with a 5 volt supply. You've got a ton of headroom with caveats. You might want to maximise the gain out of that circuit there so that you don't have to have as much processing, or so that you can maximise the dynamic range of your ADC that follows. Yep. So you might think, okay, let's make that resistor as big as we possibly can. Okay, 5 volts, 1 volt, we've got 4 volts across there. 4 volts divided by 0.35 is probably about 12k, vaguely speaking. Okay, beauty. So you go to print with that circuit.
Yep.
All of a sudden, you come along with, most of your microphones are sitting there at 350 microamps. You come along and you've got a FET in there that draws 400 microamps. Guess what? That's trying to suck 4.8 volts across that. Okay, 400 times 12, 4.8 volts. Insufficient voltage there, so instead of getting all of that lovely gain, it goes, bonk. Oh, okay, I'll cover my arse. Instead of putting in 12k, I'll put in 1k. Well, you can do that, and it'll cover all of those, but you've robbed yourself of so much gain.
Yep.
So maybe pick a resistor that allows the typical voltage there to sit at about half of your rail. This almost goes back to good old bias theory, where you try and bias things at half rail.
Half rail, that's it.
Not only will it give you the best dynamic range as far as signal excursion goes, but it also allows for production variations in that FET current.
And you want the flattest battery chemistry possible as well.
Now, the voltage rating of those FETs is generally about 10 volts. So if you were using say a 12 volt or 15 volt supply, you might want to either regulate it down a bit or resistively drop it down a bit, or do something to ensure that the voltage there stays below around about that 10 volt level, because otherwise they can start avalanching or getting noisy or undesirable effects.
And this is how, this is like the phantom voltage applied on like a PC microphone input or something like that. They will have that voltage superimposed on there, and you're supposed to hook up just the two-wire.
Not only that, they have the voltage, which is usually around about 3.5 to 5 volts, and they have the resistor built in.
Yes.
Okay, so they've done that bit inside the box.
Inside the PC.
They only want you to plug that much in.
Yep.
Now, there's yet another caveat that you have to be aware of. Okay, which is noise on this rail here.
Yep.
If this thing, if this JFET is working within that constant current region, it's presenting a very high impedance there, which means that any noise there gets presented immediately to there. So anybody who's using these from anything that might have a bit of noise there,
like a PC.
no, they're quiet. Make sure you decouple the hell out of it.
Yep. That's why PC mic inputs are so crap. They really are. They're pretty god-awful.
Yeah, and sometimes it's simply because that ground is not at a quiet place.
Absolutely.
Okay, so that's care and feeding electrically of Electret mics.
Electret mics.
It's easy.
Yep.
Get the manufacturer's spec on the mic to find out roughly what the quiescent current is going to be. Plan your resistor around that and your supply rail.
Too easy.
Yeah.
Bob's your uncle.
Not rocket science.
No, not at all. Too easy.
It's not unusual these days to see Electret mics that don't have that resistor at all.
How do they work without being biased?
I'm not quite sure. I still haven't sussed this myself. I've got a suspicion that they're actually relying on things like PCB leakage, which is up in the tens of gigohms, hundreds of gigohms, who cares? It vaguely maintains that somewhere within hailing distance of zero.
This is like trying to have a op amp like this and trying to AC couple into your...
Yes.
Like, where's the bias?
And the only real sources of bias
bias
there...
are leakage.
Well, actually, there's a couple of sources. First of all, there's leakage down through the gate there.
Yep.
And that, in fact, is a source of noise as well as bias corruption.
Right.
Now, typically, if you've got a little FET with little junctions and low capacitance, you're looking at picoamp leakages.
Yeah.
Mind you, something to keep in mind about JFETS is that leakage current will increase around about at the rate of about a decade per 10-degree rise.
Oh, okay.
So when temperatures get high, FETs get leaky.
Yep.
But it's not unusual to be talking about picoamps there. So if you can arrange for tens or hundreds of picoamps leakage to ground there by having soggy circuit board or I don't know what
trademark.
Yeah.
Soggy circuit board.
Then you can maintain the DC voltage. There's somewhere within hailing distance of zero.
Yeah.
The other thing to watch out for, of course, is that's at zero. We've got signal excursions either side of zero due to that. The negative going ones see a high impedance. Any positive going signal greater than maybe 10, 20, 30 millivolts starts to see a 4 diode junction down there and winds up being non-linearly clipped.
Ouch.
So the larger your signal, the worse it clips there. So that, we're discussing about headroom, is a headroom limitation.
Right.
Now, the other downside of leakage is it's a noise source. I can't remember the equation off the top of my head for noise current, but basically every dribble of electrons that goes down through that
That's
gate...
a genuine unit of measure.
Yeah, a dribble's worth. Every electron that jumps that barrier represents an impulse.
It does.
And the thing is, if you've got zillions of them going at once, they kind of iron out, which is why the noise of a DC current is proportional to the square root of the current. Double the number of electrons flowing through there, and the noise part of all that, those rushing ball bearings, only increases by a factor of root 2.
Right.
So it's a noise source. That current gets converted to a noise voltage by the impedance at the gate, which consists of that capacitance, that resistance.
Yep. Which will change with frequency.
Yeah, it is. But by far and away, generally the most important part of the noise is that resistor or pseudo resistor.
Yep.
Interesting thing, the higher the value of that resistor, not the higher the noise, the lower the noise.
That is
counterintuitive.
Counterintuitive.
And the reason for that is, okay, let's plot noise voltage versus frequency. For a resistor, it's basically flat, okay, equal noise voltage per unit frequency. Okay, if we double the value of resistance, we increase the noise by root 2 or 3 dB.
Right.
Okay, where that's 3 dB. Okay, why? Because noise voltage equals root of KTRB. Yeah, etc. Or KTR. So it's the fact that it's proportional to root resistance. Okay, double the resistance, increased by 3 dB only. Okay, but here we've got our resistor in series with its noise voltage source. Okay, and that voltage there increases by 3 dB there, but it's got this low pass filter attached to it. So that will only be true up to a cut-off frequency, a corner frequency determined by the value of that resistor and the value of the capacitor. So let's just say this one, okay, cut off there. Okay, so its corner frequency's there. When we double the value of resistance, we shift that down to half of what it was. So all of a sudden our noise profile looks like that. Guess what? 3 dB lower. So as long as we are only looking at frequencies significantly above that corner frequency, whenever we double that resistor, we knock 3 dB off the noise because we're in this roll-off region.
Very nice. Ta-da!
And that's part of the secret to making a low noise mic,
Yep.
is make any resistance as high as you possibly can,
Yep.
and make the capsule capacitance as high as you reasonably can.
Totally counterintuitive. Who would have thought?
Yeah, so higher resistances equal lower noise.
Lower noise.
Yeah.
That's a bombshell, folks.
Yeah. And that's why at Rode Microphones, I think I was the first one to go from 100 meg type resistances up to 5 gig type resistances. And it really paid off in making low noise preamps.
Awesome.
The other thing to watch out for is that noise current, which, as I said, noise current appears across those impedances as a noise voltage. Those impedances, well, guess what? The impedance looks like a resistor in parallel with a capacitor. The lower you can pull that down,
Yep.
the happier everybody is. And the smaller you can make that noise current, the happier everybody is as far as keeping the noise down is concerned.